So you all know that in complexity theory we are trying to prove that P is different than NP. These guys will miss the punchline. And we can't do it, so we just make our life easier and easier, and we go to different fields, simplifying the models to some extent. And one of the most interesting and successful and still largely open direction in trying to prove analogs of P that different than NP was in the arithmetic computation. So many people here are not computer scientists, which is good, but I think everybody learned 4 arithmetic operations, so that's all I'm going to use. It's what arithmetic computation is about. What can you do with this 4 arithmetic operations? We are going to work over some field, which I will not really specify. Most of what I'm going to say is true in general, or at least for infinite fields. Sometimes you need characteristic 0. Sometimes you need more. If you want to fix one, just think about the complex numbers, but where everything will be true. But all the open questions are interesting, practically over any field. So there is some field. And now we want to compute things with this arithmetic operation. So the most basic things to compute are polynomials. What's the most important polynomial in mathematics? It's the most important, yeah, it has to be useful. 1, I don't think. Yeah, that's okay, yeah. So I heard at least one friend telling me that. The determinant of an n by n matrix is this thing that's very familiar to you. Sum over all permutation pi, product xi pi. So, for example, you would like to be able to compute this thing, and in complexity, we want to ask, what's how many operations do you need to perform in order to compute this type of polynomial? You can ask this about other polynomials. There is a determinant has a very good friend, the permanent, which looks exactly, so that's an n by n matrix of variables, which looks almost the same, only that there is no sign. We would like to compute this polynomial and ask how many operations does it take. Now, when we want to count how many operations does it take, it makes sense to start defining a model. And the obvious model is just to look at a circuit of, composed of these arithmetic operations. You have the variables, x2, some variables, here we have n squared, but doesn't matter, and then we can just add them and multiply them, and so on, till we get some function in the output. I want to stress that we are talking about symbolic computation here, so what I want is that we are computing the polynomial as opposed to the function represented by the polynomial over the field. So if I wanted to compute, x to the p minus x in z mod p in the field with p elements, that's a different computation. Even though the function is identically 0 there, I would like to compute this. Okay, so the circuit model is the most basic model. You want to count the number of gates, the number of arithmetic operations you perform in this setting. And this is a circuit model. And there is also a formula model, which is a bit weaker and more popular in mathematics. Mathematicians normally, in all mathematics books, you see just formulas. So rather than having parentheses and stuff, the way we like to think of them is just trees of the same thing. So again, plus, plus times. Anyway, the graph of the circuit is a tree. What it means is that you are not allowed to reuse something you computed before. Okay, so we have circuits, we have formulas. These are the most basic computational object, computational models. And, in these models, for example, we want to know the complexity of these polynomials. And for some reason, so there'll be a lot of models or lots of settings where I will use this. The talk is about non-commutative computation, but I'll talk a lot about commutative computation. So in all of them, whenever we talk about something called, I will call P, I simply mean what can be computed by polynomial size circuits. Okay, so this is whatever, we have a polynomial, let's say, on n variables, or maybe I should say. These polynomials, you notice they are on n squared variables. I will not distinguish n and n squared because we'll care about things up to polynomials. And it will be important that the degrees are also small. So like these are multilinear polynomials, so the degrees are at most the number of variables. But let's say, so we'll just care about things that look like this. And the degree, maybe some polynomial in it. Anyway, so P will be the class of all functions that can be computed by polynomial size circuits. And for reasons I will not talk about now, NC is the class of problems, functions, polynomials that can be computed by polynomial size formula. So these are poly size formulas. And these are poly size circuits. Okay, so I want to talk about this complexity of such computations, and to organize my life, I'll write here some basic things that we will want to discuss in these various settings that I'm going to talk about. So one of the sort of messages, if you want messages for the talk, is that actually the commutative and non-commutative world are very different, and you'll see many differences. But actually, there's a lot to be gained from interactions between the commutative and the non-commutative world, and all the questions I'm going to ask are in the commutative setting and are very basic, and everybody can understand them, and I hope that some of you will actually solve them. Because it seems that, or you'll see that solving these problems in some cases give us lower bounds on non-commutative questions, on the complexity of non-commutative computations, and sometimes upper bounds in the commutative worlds give us really interesting upper bounds for basic problems in non-commutative computation. Okay, so as more or less the organization, I'll just state for the best lower bounds we know. So we'll have the circuit lower bounds, the formula lower bounds. I'll just build a matrix and we'll start filling it, and we'll see how far we go. And then we have these classes, or the NC class, polynomial size formula, the class P, and there'll be also a class NP, so all are in quotes. And of course we are interested in the, our formulas as powerful as circuits. Is P equal to NP, and whatever it means in this setting. I will not define it, but it will be clear what it is for different reasons, as you'll see, because what I'll give you is sort of complete problems for these classes. And then there'll be two more issues I want to discuss, and one is the polynomial identity testing problem, which you can think of as for the mathematicians among you, word problem for this model. It's a basic word problem which exists essentially with any algebraic structure. And I also want to talk about divisions, because so far I talked about polynomials, and I want to talk about divisions, and it turns out that will be really interesting and rich story to tell here once we move to the non-commutative world. So I'll just remind you some basic facts about the commutative computation. So here, commutative means that all the variables that we have commute. So this is the algebra is denoted. The algebra of polynomials. And we would like to prove lower bounds. We would like to prove that, the determinant is hard to compute. And actually, we know some lower bounds. So we know some n log n lower bounds here due to Strassen and Bauer and Strassen. It holds even for determinant if n is the total number of variables. So we have slightly superlinear lower bounds, and that's n is n squared. I didn't say which function, so it's explicit function. And for formulas, we know slightly stronger lower bounds. Don't remember how to spell this. Kolishenko, or anyway. There's some stronger formula, but that's what we know. I mean, we don't know any better lower bounds than this. We don't have super polynomial lower bounds. It's a great open question, and we are stuck there. But we do know some things here. In fact, Valiant in the 70s built a very rich theory of algebraic and arithmetic computation. In particular, he showed that these classes have natural complete problems. So he proved that complete problem for NCs, the determinant, our favorite function. So I'll say in a second what it means. The complete problem should be a problem that's in the class, has polynomial or roughly polynomial size circuits, but every other problem reduces to it. So I'll define it in a second. I just want to say that he proved the similar result, and very important result, that the class NP, whatever it is, has a complete problem, which is the permanent. So the permanent, this basic problem of counting matchings in graphs is as hard as computing any polynomial you can really imagine. In particular, all the counting problems in the world reduced to this one. And Valiant and his colleagues also addressed this question here and found something really peculiar that is more weird than I think we think, is that P equals NC. This Valiant, Skyum, Berkovitz, and Rakov. So anything you can do in polynomial size in formulas, in circuits, you can do also with formulas. I'm slightly cheating in general between polynomial and quasi-polynomial, like n to the log n, but since we are into exponential gaps, can allow me that. So something which we don't expect in the Boolean world. This really means that everything that can be computed efficiently sequentially can be also parallelized efficiently. It somehow happens in the commutative arithmetic computation. We don't think it happens in a Boolean case, and we'll see that it doesn't happen in the non-commutative case. Okay, so let me define what I mean by a complete problem, if you've never seen it. Somehow the nice thing about the arithmetic theory that Valiant developed, this Valiant and Skyum, is that it's really convenient to talk to mathematicians about it because there is no need to define any computational models. It's just about linear projections. So what you say is that the polynomial f reduces to a polynomial g in more variables if simply f equals g once you substitute for the variable some affine forms. So the AI are affine. Just a projection. And in particular, so that's a notion of reduction. Clearly, if you have a circuit for G, then you can build a circuit of essentially the same size for F. So that's a good notion of reduction. And this statement, for example, this completeness statement, when you spell it out in this language, what it says is the following. Assume that F, some polynomial, has a formula of size S. S size formula. Then f of x is, there is an S by S or 2S by 2S matrix filled with affine forms here. So Aij. A matrix like this, and if you take let me write the 2S here. If you take the determinant of this matrix, what you get is the formula you wanted. So everything projects to determinant of roughly the same size. Everything that has small, short formulas. And the same holds for the permanent. Any polynomial in NP, whatever it is, projects to the permanent in exactly the same way. And this is really convenient because now you can express the P versus NP question just as a question about linear projection between permanent and determinant. So P versus NP in this case. So what is P versus NP? In this setting, it's just a question whether the permanent on n and by n matrices reduces to determinant. So P equal, let me write it like this, P equal NP exactly if and only if determinant M for M, which is some polynomial in N. So many of you know that there's a new project, the project is not so new, it's probably 15 years old, that Malmali and Sohoni started to try to prove this using what they call geometric complexity theory. And actually this topic will come up again later in this talk in a somewhat weird way. But for those who are interested to know what's the best known, is there is a result of Mignon and Rassair showing that this M is at least n squared. So we do know something, although if you think about it, that's exactly what the linear lower bound would be. But anyway, so, okay, so we covered this, and of course I'll have time for exactly a quarter of what I planned. What's the polynomial identity testing problem? So what would you like to know? I give you a circuit. What's the worst problem in general? I give you a description of an object in the algebraic structure, and you want to know whether it's zero or whether it's identity, whether it's a trivial element. So here I give you a circuit or a formula, and I ask you whether it is computing the identically zero polynomial. Okay? So that's a basic question. And because of this translation here, it's the same question as I give you a matrix with variables, and I ask you whether the determinant is non-zero, whether the matrix is non-singular. And this question has a very easy answer if you allow yourself randomness, right? I mean, you can just plug random values to the variables and compute the determinant, so you don't have to compute a symbolic determinant, you just compute a numeric determinant, and you know the answer. So this problem is, at least in BPP, so, which means probabilistic polynomial time algorithms can determine the worst problem in the commutative setting. The great stories and connections to tell between this problem and circuit lower bounds, they are more or less equivalent, finding deterministic algorithms here and proving lower bounds here, but I'm not going to go there. I'm going to go in a different direction. Finally, I just want to mention the issue of division. So in the commutative setting, what is division? So here we are interested in the field of fraction, which we usually denote. But we know that this is just, the elements here are just ratios of polynomials, P over Q, right? This is what rational functions are in the commutative setting. And what's really beautiful, and again, we'll come back to this, is that Strachan showed in the 70s that, so you can try to compute a rational function by computing the numerator and the denominator separately. And the question is whether it costs you more than, because then you're computing it without divisions. The question is whether it costs you more, and its result is no. It's up to polynomial the same computation. So you might as well, if you're in the commutative setting, you might as well just deal with polynomials and forget about division. It can be eliminated efficiently. So here we have efficient elimination. Okay, so now, questions. So now I want to move to the non-commutative setting. And I want to talk about polynomials. So here we have what's denoted usually with these triangular brackets to say that we mean non-commuting variables. Okay? So we want to, everything stays the same. Of course, whenever you multiply elements, you have to say who's on the left and who's on the right. and you want to compute polynomials. Which polynomials? For example, these polynomials. But again, when you specify polynomials, you better say, the order of elements in a monomial are important.
Are the sums commutative?
Yeah, sums are commutative. Although you can go there too. No, sums are commutative. And, you can ask what do we know? So what do we know? The same lower bound in the commutative. So I should stress, the commutative setting the non-commutative setting is even more restrictive. It's harder to compute everything that you can compute commutatively. You can compute anything you can compute non-commutatively. You just forget about ordering and you can compute commutatively. So lower bounds translate. But here, for the first time, we have a real lower bound. And this 2 to the n, lower bound of Noam Nissan, and this about 30 years ago. So for formulas, we can prove exponential lower bounds for if we are in the non-commutative regime. For which polynomials? Well, for example, for determinant, for permanent, and even for functions in P. So there are functions that can be computed by circuits, by non-commutative circuits of linear size, which require exponential size in the non-commutative world. And so here we have P.
Determinant is not in P?
No. It has it's not in NC. It's not in NC. These are formula lower bounds.
But it's a local question.
Yes, exactly. Right, so we have no idea, so let me just write it. We do know this. Right? So formulas are weaker than circuits. But we don't know whether determinant can be, we'll soon say something more about it, but okay. So we have an exponential lower bound, that's great. This 30 years ago, nothing happened. Yeah. So question? No. Nothing happened since. We would like to prove circuit lower bounds, and we don't know how to do that. And I'll suggest a way to do it. But let me just complete this story here. It turns out that you can, so here I wrote these complete problems for, and in work with Hrubesh and Yehudayov, what we call the highway paper. We showed that what Valiant did extends to the non-commutative world. So the determinant, there is the same reduction as there. There's a similar reduction. Everything that has a non-commutative formula can be projected to a non-commutative determinant. When I'm saying non-commutative determinant permanent, in the usual ordering, let's say in the row order, just the way it's written here. And similarly here. And it was somewhat misleading because, we more or less realized that what he did can be converted very easily to the non-commutative case. So we again seem to have the same complete problems. But why is this misleading? So let me not write it down, but tell you about one of the really neat approaches to compute to approximate the determinant over the integers, for non-negative matrices. So we know it's a hard problem, we cannot compute it exactly, and we might be interested in approximating the permanent, let's say counting approximately how many perfect matchings the graph has. It turns out that there is a beautiful algorithm using Monte Carlo methods by Jerome Sinclair and Vigoda. But there's another completely different way of doing it that was initiated by also Alistair Sinclair and Mike Luby and Lars Rasmussen, and continued with Alistair and Steve Chen, which tries to approximate the permanent of a non-negative matrix by a reduction to computing some non-commutative determinant of some random elements from a large Clifford algebra. And the whole complication is mainly boiling down to estimating variance, which they showed that works. So everything should work, except that you need to be able to compute the determinant of a matrix of matrices, right? N by n block matrix of n by n matrices. And that they didn't know how to do, and in fact nobody knew how to do until it was clear that it cannot be done, because Arvind and Srinivasan, just 3 years ago, proved that the determinant is as hard as the permanent in the non-commutative setting. So in this language that I use here for projection, we have sort of the reverse of what's happened here. So in the non-commutative circuits, we have that the permanent indeed reduces to determinant maybe in n squared by n squared size. So determinant and permanent are completely indistinguishable. They are both hard. They are both complete for NP. And so you might wonder what's happening here. I mean, that's certainly a hard problem, but not a complete problem. But it turns out you can make something reasonable. If you look at nearly triangular matrices, then it's still well, basically it's complete. It's still hard, and it's
Clifford algebra approach also is related to Barvino?
It is related. The whole sequence of it starts from Godzil and Gutmann, and then Karp and Karmaker, and a list of other people, then Barvino and many others. But the culmination of this was the approach of really going to large Clifford algebras and reducing the variance to what you need, that the papers I mentioned. So, okay, finally let me mention something about this. Yeah, so, yeah.
The lower bound is also called Clifford algebra.
The lower bound works even for 2 by 2 matrices. Yeah, even for quaternions. Yeah, it's amazing. It's already as powerful as yeah. What about polynomial identity testing? I give you a formula which computes a non-commutative polynomial. Is it the identically zero polynomial? The identically zero polynomial. Now, actually, you probably realize that many of you know that there are non-zero, but let's say here where the non-commutative world starts to be weird, and it will get really weird soon. There are non-zero polynomials which are zero on every sequence of elements in the field. Of course, you know this. Right? That's a non-zero polynomial which is identically zero of any element in the field. Any element in the field. And there's a more general, complete understanding of this. There's a whole theory of polynomial identities. But Amitzur and Levitsky showed that if the degree of f is at most n, then it cannot be satisfied by all n by n matrices. So then there exists, I don't know, M1, 2, n of f, but that f of this vector of matrices is not zero. Okay. So what you can do, and then once you realize this, you realize that you can, do the same randomized algorithm, and this was realized by Bogdanov and V. So also here we have an efficient probabilistic algorithm for computing the world problem. So let me now talk about proving lower bounds here. So how do you prove lower bounds here? We don't know, but in another paper, and that's one of my first open problem here, another paper with same highway guys, another highway. We proved the following thing. So we showed that proving a lower bound for a very simple and in fact classical problem. That's the main reason I chose this topic for this conference. This neoclassical thing that everybody's been joking about. I knew that I have to provide some, it's a famous movie, the names of some famous dead dudes. Those who, Anyway, I have here, for those, I have one distributed. Those who want can pick it up here, summarizing some of what I'll say and more. But there's this classical problem, which is the sum of squares problem. And everything you know about sum of squares, forget, because it's a different sum of squares problem than everybody is talking about. Holds the key to proving lower bounds in non-commutative settings. So what's the problem? Well, you will agree with me if I write x1 squared times y1 squared. It's x1, y1 squared. So far, I'm sure everybody's happy. So this is for single squares. But suppose I want to do for sums of two squares.
It's commutative, right?
Yeah, sorry. Thank you. So on this board, everything is commutative. x1 squared by f2 squared times y1 squared plus y2 squared. Is it a sum of squares? Well, of course it's a sum of squares. I can open it up and it's a sum of 4 squares, but this is a sum of 2 squares. And it is because, I'm sure if you know, x1, y1 plus x2, y2 squared plus x1, y2 minus x2, y1 squared. So it's a sum of 2 squares. This was realized very early on by many people, Fermat, but long before Fermat. So that's great. So maybe it extends. Can we do more? And I think 1748, Euler did the first, really non-trivial one. One squared so it's z1 squared plus z2 squared plus z3 squared plus z4 squared. Well, of course, the z's, you realize they should be bilinear forms. So zi's of xy bilinear. Okay, so 1, 2, 4, immediately now people saw what's going to happen, and then Hamilton, or maybe no, Cayley, I guess, well, I'm not sure, Cayley and Graves. So did the case of 8. And now everybody knew exactly what's going to happen, so they went for 16. And I think many of you know this, but they got stuck. And then the person who put them out of their misery was Hurwitz. And said only 1, 2, 4, 8. There are no such identities if you want exactly n times. You multiply sum of n squared by another sum of n squared. You want sum of n squared. Doesn't work. But it just leads to more questions, right, whenever we have. So suddenly we can denote by, let me call it S of n, the minimum k, such that when I sum n and I get the sum of k zi's, then, well, we know it's possible, right? So what's the minimum k? Okay, that's a nice question. People studied it. It comes up in several areas, not just this comes from division algebra, all these guys, but there are people in topology. In fact, this question is exactly the topological question of finding a bilinear map from Sn minus 1 cross Sn minus 1 to Sk minus 1. These are the spheres in appropriate dimension, turns out. So I can ask, what's the minimum? And people ask this, and what do we know? Well, let me put some, so this can be done over any field or ring, because we have definitely have a solution of n squared just in zeros and ones. So people studied actually mainly SR of n, and I said it's at most n squared, and it turns out to be at least roughly 2n. This is a deep result of James. algebraic topological result. Turns out that the upper bound can also be improved. It's n squared over log n. It's the result of Radon and Hurwitz. But anyway, somewhere between linear and quadratic. So it's not going anywhere in the exponential lower bounds we want. And in fact, it doesn't seem to be related because it's a commutative one. So what we proved in this paper here is the following. So we proved two results. Erase the trivial one. If you can prove over the complex numbers, not over the reals, over the complex numbers, you want to prove a slightly superlinear lower bound. And to the 1 plus epsilon for this number of squares you need, this implies that permanent n has or requires circuit size non-commutative. Circuits of size exponential requires. Okay, so all you need to do to prove an exponential lower bound is just to prove this superlinear lower bound.
Is this theorem that other than the three examples, this lower bound holds? Or?
Which lower
This
bound?
three
This
here.
one? Yeah, you're enlarged enough.
Right.
Yeah, enlarged enough. So we proved this, and then we tried to prove the lower bound, but we couldn't. The only thing we could do, which I can assure you is much easier, although, is that if you work over the integers, then there is a lower bound, n to the 6/5. So there is a lower bound. But, it's, in some sense, it's a monotone type of lower bound. So I won't explain it. Anyway, so that's the first challenge. Okay.
This is a very concrete problem.
Very concrete.
Yeah.
Yeah. So that's a very concrete problem. So I want to give you another very concrete problem that will go to the last part of the talk, which is what happens with divisions. So let me write the problem. Write it here. It's a completely different problem, so I'm switching gears. So let's call a matrix yeah, so let's look, I just erased it, but the matrices I used before for the determinant projection looks like they had some affine forms here. So we have some variables xi, and we had some aij of this vector x. So this matrix, sometimes it's called the linear pencil, for those who like this terminology. So A is really the sum of some matrices AI, so over just the matrices over our field, times xi. So that's a linear pencil. There may be a A0, like constant term, but I won't bother with this. Okay, so you have a matrix like this, and suppose, and let's call an A like this invertible, put it in quotes, if I can replace these xi's by large matrices, so that the matrix becomes invertible. Okay, so invertible in the usual sense, because I'll put numerical matrices here. So it's invertible if there exists a K and matrices, let's call them, I don't know, M1 up to M. Let's say there are n of them here. It's no loss of generality to assume that the size of the matrix and the number of variables is the same. So Mn such that this matrix, which is now numerical matrix over the field, is invertible. Okay. That's a definition. Okay. And what we want an upper bound, we want k of n, we want an upper bound. If a matrix is invertible, we want to say it can be done with matrices which are small. They are not that large, given n. Okay? So we want to say k of n is the smallest integer, so that whenever the premise is true, we can take k, some k, which is at most k of n. So there are always matrices with this small k. It's a question. I would conjecture, and so I'll tell you some stories about this. Let me conjecture, even though it's just a question, we don't really have an intuition for it, is a polynomial in n. I will not have time to tell you all the stories I want to tell about this. I want to explain how it's coming from this non-commutative world, but this is now a commutative question, right? I just said whenever you can replace them with large matrices, you can replace them with small matrices and make it invertible. So it's not a commutative question. It's studied a lot in commutative algebra, this type of question, and in fact, I don't know, some people here would recognize, Terry should recognize, that it's related to the GCT question, to the geometric complexity theory question. It has to do with the so-called Kronecker coefficient problem. I don't know how many people know here about this problem. It has to do with understanding certain questions in representation theory, and people in algebraic geometry and invariant theory are trying to prove this kind of thing. So now I want to tell you, we don't work in this area. So this, from now on, I'm talking about some recent work with Hrubesh. We arrived to it in a completely different way. So it turns out, if this is true, then some things in the non-commutative world, become efficient. So let me tell you which. Questions? Right. So I'll go, so we need to move to the world where we are non-commutative and we have division. So what is this world? So the first thing you can ask, is what happens, can we eliminate division in, or what, in fact, what are these, what's the analog of rational functions here in the non-commutative world? So let me just give you some examples so you'll see how weird this world is. So, do I have 10 minutes? Or not? 5 minutes? Yeah, 5 minutes, yeah, whatever. So I'll just give you some examples and I'll tell you what. If I write, we are in the non-commutative world. If I write, in the commutative world, we said everything is a ratio of polynomials. If I write x inverse plus y inverse, you can really convince yourself that there is no way to write it as a ratio of polynomials. So, not everything is a ratio of polynomials. You can look at, I don't know, this cannot be written as a ratio of polynomials. So you say maybe you can, you can think these should be your monomials and you should expand or something like this. So here's an interesting one. So suppose I write x plus, xy inverse. X inverse. Is there a nested inverse? I mean, we can write expressions using plus times divide and multiplication and division, but the question, how do they simplify? And it turns out in this case you can remove the nested inversion. This is in fact a famous identity. It's called the Huaz identity, which is underlying what's called the fundamental theorem of projective geometry. So there are, some weird simplifications of nested inversion. And you can wonder whether you can do it in general, but it's a highly non-trivial fact that if you write a similar expression here, z, y inverse w, and you take inverse again, then you cannot remove this nested inversion. It's impossible. And in fact, one of the most important theorems in the field is of Rethenauer, which says that there is a, this inversion height is infinite, the inversion height hierarchy. So the number of steps you can, there will be expressions that you cannot simplify with any number of nested inversions. In fact, he proves a stronger theorem. He proves that, he tells you what is the hardest in some sense, rational expression. And actually, you think about it, we said, I asked you in the beginning, what's the most important polynomial in the commutative world, and some people said determinant, and I agree. So what's the most important polynomial or rational function in the non-commutative world? Determinant, we looked at determinant before, but it's clear there was an arbitrariness in the definition of order of monomials, and in fact people struggled with it for many years, and yeah. What do you ever need rational functions for? You need rational functions to solve linear equations, right? I mean, if you want to solve ax equals what? Ax equals b, you need to invert. You need to invert A, or if you want to solve a linear system, you need to. So matrix inverse turns out to be the most important, not rational function, it's a set of rational functions, one for every entry. So what Rethenauer proved, that if we take an n by n matrix and invert it, and we write the entries as rational functions in the original entries, this requires height n. And I'll just, now that I am running out of time, I'll just fill the entries without telling you too many details about these things. Some things follow from this and others, don't. But here's what we can do in this paper with Rubesch. So it turns out that because of this fact, and because even in the non-commutative world with division, formulas can be balanced, we can get an analog of Nissan's theorem here. So we can get a 2 to the n lower bound even for functions in P. And in fact, the function in P is this function, x inverse. So inverting a non-commutative matrix generic has polynomial size circuits, but requires exponential size formula, which goes back to Alistair Sinclair's and all the other guys' approach to approximate the permanent. Maybe what you need to do is not compute determinants. You should compute something which is computable in the non-commutative world. And use the inverse of a matrix of maybe block random Clifford algebra. We tried it. I know we couldn't do it. But anyway, so you can prove lower bounds here. So I just want to tell you what happens, what does this problem influence in this world. And what it influences are these two things, the last two things. I give you a rational expression. Is it the identically zero expression? That's the worst problem. We don't know. But if the answer to this conjecture is true, then so the conjecture will imply a BPP algorithm. What about elimination of division? We saw that in the commutative world it can be done for free with polynomial overhead. We don't know, so I should say that this is open, but that's what will happen. Also here it's open, but if the conjecture is true, then there will be an efficient elimination. So up to polynomial factors of division. So let me stop here. Thanks. I don't know what happens over R. Well, no, I know what happens over R in that we can prove lower bounds over R, not for this problem, but for some other explicit polynomial. You can see that, maybe it's not obvious, but this particular polynomial, the sum of squares of the x's and sum of squares of the y's, it's a particular polynomial of degree 4, biquadratic polynomial. We said that lower bounds for it, superlinear lower bounds for it, will imply something when it's over C. Over R, it doesn't imply anything, and in fact, we can prove an n-squared lower bound for some other biquadratic polynomial that's explicit, that will have the same purpose if it was over complex. But what I can say is that you don't need to prove the lower bound over the complex numbers. It's okay if you do it even over the Gaussian integers. Somehow, I mentioned that our lower bound over the integers, over the reals, is a monotone lower bound. It's a monotone lower bound because the square root of -1, when you square it, becomes -1 and allows you to do negation. And that's what you don't have in 0R. So that's the reason, anyway, so that's what we know.
Does it make sense to interpolate between the commutative and non-commutative case by imposing some relations? I mean, for example, if you think of computing, say, basically expressions in a group algebra, some group, some relations.
It makes perfect sense, and it was in fact studied a lot in some of the contexts that I mentioned. So, for example, in this proof that determinant is as hard as permanent, initially what they proved it is for the generic determinant over free variables. But then, subsequent work, I think, Alistair, it was you and Chen and Arvind and Srinivasan, right?
Prahlad.
And Prahlad, yeah. Proved the same, even if you have, lots of relations. Based very, very specific group algebras. In fact, I mentioned quaternions or 2x2, and they characterize, and for some, of these non-commutative algebras, there is, it's not this powerful. So they know more or less exactly. So it makes perfect sense, and it was studied, yeah.
Is there a topical computation complexity?
And, it's a good question. I mean, I don't know, but probably we should start it. Yeah.
So for the complex problem, you need all the terms to be bilinear.
Yeah, all the terms are bilinear.
Otherwise, it's sort of a
Yeah, I should mention here something really curious, which is related in some sense to Hamed's talk in the morning. You can ask in an infinite field, if the ZIs are polynomials, then they might as well be bilinear. It's very easy to see. But you can say, suppose they are not polynomials. Suppose I allow them to be rational functions, just like with Hilbert and Artin and everything. But it turns out that if you allow the ZIs to be rational functions, then you can have identities like all these 1, 2, 4, 8 for every power of 2. So if you replace this bilinear by rational function, then there is a Pfister theorem, which says that you can have any S of n equal n. Beautiful thing. In fact, these handouts which have all the identities up to 8 also have, it's the first page of a paper explaining this rational functions, so those of you who want to see it.
But does that self-reference? So could you start on the left with the x's and the y's being?
With the x's and the y's being rational functions? Yeah, it's commutative, so because in the commutative world everything is simple, then the answer is yes. Yeah.
Okay, so that's it for questions. Is it 20 minutes break? 20 minutes break. No, that's not going to